All right, so this video is going to discuss the patterns of logarithms. The first pattern of logarithms that I want to take a look at, and actually a couple of patterns, they start with an exponential property, right? So the first property that we want to take a look at is, let's say, let's go with anything. So any number raised to the 0 power we know equals 1. Right, so any number, regardless of what it is, like 75 raised to the 0 equals 1, or negative 212 raised to the 0, all of it, no matter what it is. So any number, or variable for that matter, anything, if we raise it to the 0 power, it's going to equal 1. Now, let's take this and switch it into logarithmic form. So our base here is a, so if we switch this to logarithmic form, we could say log base a of 1 equals 0. So this pattern says that regardless of what my base is, if the argument is 1, then the whole thing is going to be equal to 0. Right? So no matter what the base is, if my argument is 1, then the whole thing is going to set equal to 0. So for example, if I had log base 17 of 1, that equals 0. And I can play this game all day. Log base 42 of 1 equals 0, right? So anytime I have a 1 as my argument, the whole logarithm then is going to be set equal to 0. This saved me a ton of headaches in college algebra and calculus. This particular pattern saved me a ton of headaches. And it took me a while to get used to it, but I just remembered anytime I have a 1 in the logarithm, right? A 1 in the logarithm, that means that the exponent would be 0, right? Because anything raised to the 0 power equals 1. So that's our first pattern, is this guy right here, right? Doesn't matter what the base is, but if the argument is 1, then the whole logarithm is going to be equal to 0. Okay. So that's a really good one. What about another exponential property? It's not really a property so much as an understanding, right? Well, we could say that any number raised to the first power equals that number, right? So like 17 to the first power is 17. Negative 45.62 raised to the first power is negative 45.62. It really doesn't matter what that number is. As long as we raise it to the first power, it's going to equal that number. All right, so what happens if we switch this into logarithmic form? Well, my base stays the same, so then I can say log base a. And now the answer of exponential form is the argument of my logarithm. So log base a of a equals 1. This is important. So if I had log base 7 of 7, that's 1. If I have log base 9 of 9, it's 1. It doesn't matter what that number is, as long as the base and the argument are the same. The base and the argument are the same. So here is our second cool pattern that we get with logarithms. And again, this one saved me a bunch of effort. And we're going to see this show up again a little bit later on in what we do here in week 2 of our quarantine. So this one actually, this pattern is going to show up a little bit. This one as well show up sometimes, but really it's, you know, these two guys right here, these patterns will show themselves. Another pattern that we have that we kind of got from last week, it kind of hinted at this pattern. This pattern, so if I have the log base a of a raised to another power, we'll call it x, that all equals x. And it's really easy to figure this one out, right? If I take the exponential property, right, where x comes out front, then I would have x times log base a of a. And as we just saw half a second ago, log base a of a equals 1. So all of this would equal 1. Clearly, x times 1 equals x, right? So x times 1 has to be x. So it's a quick little easy proof. We already know this one, and it's kind of a corollary of this pattern here, okay? And we saw that in the first week as well. Okay, now there is something super cool. This pattern that we're about to show here and discuss here, It's a really neat pattern, and you're going to hear this one quite a bit in college algebra. And this one, I think, is probably the easiest one to remember. It's easy to get confused, so make sure you pay mighty close attention as to how I got this. Well, I guess less on how I got this and how to use this next pattern. And this next pattern is called the change of base, right? And it's a formula that we're going to get. It's change of base. Okay, on your calculator here, the standard TI-83 plus only gives us log, which is log base 10, and natural log, which is log base E. Those are the two most commonly used logarithms. Now, why doesn't it give us log base something of something else? So here's how this works. It starts with the definition of the logarithm, right? So the definition of logarithms, it says if a to the x equals b, then log base a of b equals x, right? So that is our definition of logarithms. This is the definition that we got on the very first day. This is what it says, how to switch from exponential to logarithmic, how to go from logarithmic to exponential. This is the basis for all things logarithmic. So all things logarithms have to do with this, right? Okay, I'm gonna set that aside for just a second, and let's take a look at the original. If I have a to the x equals b, right? I'm starting right here. Now, what happens if I choose to take the log of both sides? And I'm going to choose log base 10, right? Because I get two logarithms on my calculator. I get 10 and e. And I'm going to choose log base 10 because that seems to be a little bit more familiar with everybody. And I'm okay with that. So here, I'm going to take log base 10 of both sides. So I'm going to say the log base 10 of a to the x equals log base 10 of b. I can do this because what I did to one side, I did to the other. Also, no matter what, as long as the bases are the same, then the arguments must be equal. So I didn't break any rules, mathematically speaking, and this is actually going to be a step that we're going to need to use later on. So now, all I did is I took the log of both sides. Now I can take advantage of this. Now I have an exponent here, right? That x is an exponent. So I'm going to take advantage of the exponential property of logarithms, and I'm going to put that x right on out front. So I get x times the log of a equals the log of b. Okay, so far so good. Now, the log of a number is a number, and I will always treat it like a number. The log of a number is a number, and you treat it like a number. So here, what I'm going to do to get x by itself, I'm going to divide both sides by log of a. So log of a. And now that's going to cancel, and I'm left with x equals the log of b divided by the log of a. So now I have x by itself here, where x equals the log of b divided by the log of a. But sneak back to the original definition of logarithms. The log base a of b equals x, right? So if log base a of b equals x, I'm using the same exponential form to start with, and I get x equals log base 10 of b divided by log base 10 of a, well, if this equals x and x equals that, then that must be that log base a of b equals log base 10 of b divided by log base 10 of a. This, my friends, is called the change of base formula. That is the change of base formula. So log base a of b is equal to log base 10 of b divided by log base 10 of a. And what's really cool, I chose to use log base 10 when I took the log of both sides. I could have used the natural log. And so, consequently, I could also say that the log base a of b is equal to the natural log of b divided by the natural log of a. This is the one you're probably going to use, and that's A-okay, and I want you to. Let's take a look at a few examples that we're going to come across in some of our practice problems. So the first thing says, use the change of base formula and round your answers to the nearest 1,000. Okay, so here I have log base 4 of 19. Well, the change of base formula says that the log base 10 of 19 divided by the log base 10 of 4. So then I go to my calculator. I get on my calculator. You can see that barely. I'm sorry. All right, so I'm going to start with log base 10, right? So log base 10 of 19, close parentheses. It's really important that you close those parentheses. Then divided by log base 10 of 4. So log base 10 of 19 divided by log base 10 of 4, what do we get? We get this whatever number, 2.1239, going to the nearest thousandth, so it's 2.124. So this whole thing equals 2.124. All right, let's take a look at another one. Take a look at another one. Here we have the log base 7 of 492. All right, so I'm going to plug that in my calculator as log base 10 of 492 divided by log base 10 of 7. All right, so getting my calculator out, I go, here we go, log base 10 of 492 divided by log base 10 of 7. And that's what it's going to look like in my calculator. Okay. And then I hit enter, and it spits back a 3.1853, so 5. Now, you're probably thinking, Mr. Steven, I don't have one of those calculator things. So what do I do? Great. So when you're dealing with something like this, all right, my suggestion is to go into Desmos, right? So here we are. I'm going to go to desmos.com. So let's go desmos.com here and start graphing. Great, cool, neat. All right, I don't need that. I could just use this side as a graphing calculator. So I'm going to go over here and let's take a look at the logarithms that they give me. So I go to functions and I go to miscellaneous, and it gives me log, log A, log, and natural log. All right, so I'm going to use the log base 10. So the next problem was log base 6 of 3. Actually, you know what? Let's do the last one. Log base 7 of 492, the one we just did. So I could type in log of 492, close my parentheses, and then divide that. So I'm going to go divide by, and then I wonder, can I just type the word log? I bet I can. Log base 10 of 7. And we got the same number back out, 3.1853, and then that goes to 3.185.